All right, guys, hopefully everybody had really good lunch. So our next speaker is a distributed systems engineer at Twitter. And he wrote a blog post a while ago that I actually read and I thought was very, very good because it put distributed systems in language that was easy to understand from a developer or ops perspective. It's notes on distributed systems for young bloods. So his talk is going to be focused around the heavy lifting required of getting distributed systems into production, having them in a state that you can actually use for whatever your business case are. So it's Jeff Hodges.
I'm on. There, yeah? Hey! Cool, did too much scotch. Okay. This talk is mistitled. What we're actually going to be talking about is a single distributed system, because your systems are built up of systems. There's only one, the big thing overall. Okay, and first I want to tell you why you should listen to me. You should listen to me because I've been at Twitter for a while, and I've been at Twitter for long enough that we were an immature engineering organization that grew into a much more mature, disciplined, and responsible one. And I started as a irresponsible, undisciplined noob of an engineer at Twitter and got to grow along with the company. That's been really exciting, and I've gotten to learn things that I don't think I would have gotten very many other places to learn at, which is great. And so you should listen to me because I've done some stuff. But you should listen to me for a whole bunch of reasons. Probably about maybe a third to almost the half of the room will have more machines than we do. The other half to 60 or 70% will have many fewer machines than we do. And so there are a whole bunch of lessons that maybe don't apply, or maybe used to apply, but no longer do. And so we need to pay attention to that as we're working through this. But you actually should still listen to me, because a lot of these problems and a lot of the things I'm going to be talking about are scale invariant, that they're actually becoming what it means to be shipping code in the industry today. I mean, like, we can just talk about EC2 alone. That becomes a very large distributed problem. In fact, we've had distributed problems for as long as we've had web apps and databases. But those have just been really well known that we don't consider them that. It's kind of like how we call search not an AI problem, but it's still kind of like artificial intelligence. We just don't consider it that because we're common, we're used to it. Did it just drop off? Okay. So I was asked over Twitter, I took a little feedback, and I asked for, what do you guys want to hear? And somebody said, hope. They wanted to know that they could actually get this done, and that they could actually work and understand what their systems were doing. And I was like, okay. So first off, the first thing you do is that most of the things that you do are fine. You can just do the dumbest thing. This works for a variety of problems. It works at a variety of problems at Twitter. It works at problems at Amazon. It works at problems at Google. I should have some of you guys talk about S3 and how it works and how we do some of our stuff at Twitter. You can actually, for a wide variety of problems, you can just do the dumbest smart thing that you can think of, and that works. It's actually, you need to actually know the problem and pay attention to it, but it works. Okay. The other bit of that hope is that people have done dumber things than you. People still today ship with this protocol called shoot the other node in the head, where if there detects a problem, the other node gets killed by that node that detected the problem. That usually causes more outages than you would think. A lot of these reconciliation things are not reconciliation, but are mostly just kind of a bad idea that's lasted for too long. Sorry if anybody's shipping that today, but don't. Of course, if you're doing dumber stuff and you've been doing it for a while, it's actually harder to start doing the right thing. It's kind of like when you don't exercise and you start trying to come back in, your body hurts a lot, and it takes longer for you to build up those muscles. If you start from the beginning, the more you do, the better off you are. But it's a trade-off, and that's why this is actually the hope section. It's kind of hope, and it's kind of yeah, you have a bunch of problems as well. Okay, so how do you know if a software engineer used to be a physics major? They'll tell you. Hi. And physics, and specifically special relativity, talks about light cones. And light cones are the part of space and time that you're actually able to reach from the point that you're at right now. Let's suppose we were a photon. You see those two 45-degree angles like that? That is the most amount of space that that photon can cover in the time allotted going up. And of course, you have the past and reverse. And so there are spaces on the right-hand side over here that are uncrossable, that there is space-time in which communication cannot occur, that there is no information traversal possible. And that's why distributed systems, in part, are hard. It's one of the very many reasons. We're going to get to another one later on. But what this tells us in a real way is that concurrency is normal. It's the common case. It's not the unusual case. You don't have a single writer in a lot of places. You don't have an ability to just take a lock and just do whatever you want. There are additional protocols that you need to build in place in order to handle those things. And that is something that, as we're productionizing our systems, we have to be thinking about before the first line of code ever gets written, or at least somewhere before we start giving users to it. But I'll get to another trick that lets you play some of those games later on, too. And what that also means is that since the system itself can't communicate with each other, with the parts in between, we have to know what the system is going to do and what it's doing better than it does. We have to understand what its plan is and what we're going to do with it. And to that end, it's slow is the hardest thing you'll ever debug. If you saw my blog post, I'd rip this straight from it because it's actually one of the most important, I think. If you've not shipped a distributed system at your company, or you've shipped one or two and you haven't yet seen all the things that you'll see, the hardest problem that you'll have is another engineer or a PM, or God help you, a user, coming to you and saying, it's slow. And you're like, what do you mean slow? And they're like, well, I wrote a thing and I posted it and then it took forever. And you're like, oh, okay, that's like 20 different systems. Let me walk through each individual piece and to figure out what the slowness is. And that's hard. It's because it's delocalized. There is no one place that it's slow exists. It's at every level of your stack. That sometimes includes your kernel, which we all kind of take for granted, but it is a thing. And now a lot of people, when you talk about slowness, they start talking about profiling. And profiling is cool, and you should totally do it. You should do profiling, you should do load testing. They're awesome. They're brilliant. They're great things. But they don't solve the problem of being able to introspect into your system the way you need it, for two reasons. One, problems in distributed systems tend to be transient, and they tend to be dependent upon properties out of the universe that are outside your control. For instance, you can have in Japan, there may be a time in which everybody in Japan decides to tweet the same word because there's this very popular anime that plays every year. And most of your system can totally handle fine, and maybe you just have this one weird little search nobbin that doesn't really handle partitioning on words very well in Japanese when they're all the same. And you have problems. But those are things that you can't see from a profile. Because one, you won't necessarily have a profiler running because they tend to be heavyweight. And even the low weight ones tend not to be working across many machines all at once, which is what you really need. You need a full trace. And lastly, profilers tend to average out behavior when you're actually looking for extremums. Jeff Dean's going to give a great keynote where he's talking about the extremums really, really well and handle SLAs. And so while his talk will be on designing systems ahead of time, I'm going to be talking about how to figure out where they are now. And so profilers average it out. You just get to, and so if it's a transient thing that only happens on one machine or for a couple pieces of data, you don't know. So you need metrics. Okay, cool. There's a really, really great talk that I'm going to be a hyperlink to that you just go watch. It's called Metrics Everywhere. It's from this guy, Coda Hale. He will tell you more about business value and metrics and everything else than you could possibly understand. It's great. But metrics are the way for you to introspect continually on an ongoing basis and asynchronously while you're not even paying attention to the system, introspect into it by having a series of charts that go through. Some of you are familiar with this idea already, but some of you are not. You actually need to expose in every process that you run stats about how many tweets it's handling, how many requests it's handling, what's the latency to the database, latency to this other system, how long it took to go through each individual stage of your system. Without it, you will not be able to ship to production. You will not understand what is going on. There is a mental gap, and I'm stealing directly from Coda right now. There's a mental gap between what we believe our code does and what it actually does in the world. And that mental gap is crossed through the use of metrics. There are entire libraries that we have had to exclude from our use because there's no way to stack them. That we actually need to understand what is going on. And this took a really long time for us to figure out in some cases. And sometimes if you don't start working on it early enough in part of your project, you not only have the software problems of getting those stats everywhere, but you also have the cultural problems of paying attention to them. And like you actually need to address that early on in the lifetime of your systems. And I'm going to do a couple of brief sidetrack things. You just need one overview. You should definitely have a bunch more interesting pages with interesting data. You should have the ability to dynamically pull metrics whenever you need it and slice and dice it in whatever way you need, offsetting one graph by 24 hours to see what it's looked like, or at least being able to tab between two pages, doing this whole thing. Stuff that we spend an enormous amount of resources on because it's actually been a huge game changer for us and something that we really appreciate. And one of the things I think actually sets Twitter apart in terms of observability. But what you really want is to be able to know how your system is doing at any given time at a high level. You don't want multiples of these because human beings are human beings, and they will either look at different ones depending on who you are on the team. You know, guy one will read A and B, and then somebody else will read C and D, and another person will read E and F, and they'll have a different idea of how the system behaves and how it works based off what they've intuited. By having one big giant overview, you can at least agree on what's going on in the system. And you'll get a better idea. Of course, you should be churning through that. That is an ongoing process of what the important metrics are that should exist on that page. Not too much, but a little bit. And lastly, this should say releases. Releases should change a metric. When you release code, you should be changing a metric somewhere that you can actually graph. When I worked in trust and safety and anti-spam, I got to, I'm going to mispronounce the word, but it's Schadenfreude graphs? Schadenfreude graphs. They were great because it was a graph of somebody that was fucking out of a day job. It was awesome. We were putting out a business spammers as that thing went up and to the right. And that's the kind of stuff like we could do with every release and every deploy of code. We get to see how our system was moving and what it was. And that was the difference between a long period in which spam was a problem on Twitter and where now it has at least been reduced in effect by a great deal. There used to be entire whole things. It was really exciting to work on that stuff. But deploys and releases, if you release code that you say does something, but it doesn't change anything, what is it changing? Because distributed systems are built because none of any of us tend to expose in our use of it all of the edge cases in the app. Like I use Twitter differently than everybody else uses Twitter. People use Salesforce's CRM, but not the file upload. And without being able to have a deploy and seeing how your users are changing and how their stuff is working, you don't know. Metrics are how you get this job done. I could talk about this for days. Okay. Now I'm going to talk about a little bit what they're talking about in that room, which is debugging production systems. And the first trick that everybody actually has to get across is that you really, really are correlating by time. That's it. We have a fake idea of what causality is, which is we have to look at metrics at one time period and compare them to another time period and see if event A maybe led to event B. And this is it. This is the basic. We don't talk about it explicitly a lot, and I feel that we're actually missing out as an industry by not being, really, we're faking out this correlation causation thing, and we're going by time and metrics. And so now a lot of people are like, whoa, wait, there's this other thing that you can use called logging. And you can log data out and you can know what everything is doing. And a free-form log. I don't mean like a structured log that's like all of your requests. I mean like a free-form, we'll log out every time we see a tweet come by and we'll say what user it came from. Okay. A couple things though. Logs are liars. I have seen so many incidents get prolonged because somebody read the logs and didn't check the metrics. There's a couple of reasons why logs are liars. Common problems get overlogged. We had a thing where when we booted up and we looked at our service discovery stuff, if the file path didn't exist in the other DC, we would throw an error. But that was a common case. That was totally normal because we weren't in the DC yet. But you would look at it and you'd go, oh crap, everything's broken. And you would miss the actual thing that was broken. That was maybe one line, if you're lucky, buried in the middle of the logs because you have all this crap filling up your stuff. Engineers tend to be bad we're all very bad at guessing what the real problems are. And mostly, when it comes to edge cases, we don't log the edge case, because we didn't know the edge case existed to be logged in the first place. Why would it be there? So instead, you have to apply metrics to the problem. Because at least there, right, somebody just said yes, I'm really excited about that. You can at least apply differences, because if you missed, you have stage A, B, and C, and you missed a metric that's important in stage B, and you have a problem where stage C's numbers are lower than stage A's, you can at least correlate and see that there's a missing gap here. And you know where the problem is instead of being somewhere out in this big giant fleet of machines that may only be 10, but that can be 10 machines, can be a lot of machines for like one engineer. And so, I already talked about that, but metrics, of course, can also lie. And I have a quick story about that actually just happened a couple of weeks ago. We had an engineer come over to me while he was having an incident, and he's like, I don't know what's going on. We have this huge network latency that is just killing us. And I'm like, network latency? What do you mean? He's like, look, we're talking to like this user service, and we're talking to Memcache, and this other thing, and like they're all super slow. It's like taking like seconds worth of data to come out. And it seems to be like it's across all the services, and it's network. It's got to be just these machines. I'm like, we're here in Mesos, right? And they're like, yeah. So we're like scheduled on different machines, and okay, so it doesn't. You know what? Show me what your garbage collection stats. Show me what those look like. And of course, in the JVM, and most garbage collectors have a stop the world phase, where they stop all of the threads while they clean up all the garbage that's been created over time. And their app had some architectural problems, and they had something like 10 or 20-second pause times, where their app was just no longer responding, but they were like young engineers who were just coming up in the world and didn't know to look for that. Because, I got to discover that like 3 years before them. Good job, me. But that's the thing that happens. You can totally, by misinterpretation, you can misinterpret logs, but they're much, much easier to interpret correctly than a log, than a free-form log. Okay, and then of course, you guys are probably familiar with alerting. You get emails or pages whenever something goes bad. Don't do too much of this. If you're paging and the alerts are not actionable, and you can't do anything about them, you should just delete them. Don't get the email, because you'll just make everybody so common, they'll make them so used to the emails themselves that nobody will pay attention to them. I've seen a ton of incidents that could have been cut off 10 minutes in, take an hour or two, because nobody knew that this one email was now an actual real email instead of being the bullshit that they've been watching before. By the way, this is really good scotch. It's really good. So, yeah, you're jealous now, right? All right. So because you're at RICON, you're probably familiar with the idea of partial failures. Partial failures being where instead of the entire system going down, you have a part of it going down, or just getting slower, like the it's slow that we talked about earlier. You have a machine or two go down, or a thread in a process somewhere. It just fails and crashes, and you don't know. And so partial failure is one of the things that I think actually, when I was asked a long time ago in an interview, what do you think makes distributed systems different? I said latency. And they're like, yeah, that's one of the things that I like worse. But the real thing is failures. And they walked me through this whole thing about how in a single machine system, failures mean the thing went down generally. Or at least you know that it's localized and where and what machine it is, and you can attach a debugger to it and figure that out. Partial failures show up as delocalized, decentralized behavior that may take 3 system hops before that actually causes a real problem. Partial failures are a trick. However, because we get partial failures, we also get this other thing called partial availability. And that is awesome. Partial availability is one of the godsends of distributed systems. And I'm going to talk quickly about a couple of the examples of it. And this is how you should be building systems, is thinking about partial availability. When you're productionizing, your shit will go down. It's okay. You're not a bad engineer. You might be a bad engineer, but you're not a really bad engineer. It will go down. The cleanest, best example is search. Inktomi did this way back in the day. Twitter does this today. It's really common. Everybody does it. Your data set doesn't fit onto one machine for your search index, so you partition the search index by some means. And you say, okay, I've got some in 5, let's call it 5 machines, and they've all got a part, or maybe vnode slices of the same index. And so what happens is they query, whenever you do a search query, you query all of those machines, a covering set, and then you pull back the results, and you get some in from each of the machines, and then you take that in and you mux them together and you sort them by relevancy, and you take the top M and you send those back, and those are your most relevant results. That's search. It's great. What's really great about search is that it can be easily and trivially partially available. If one of those shards goes down, you can actually still make pretty good results with the other 4 shards. And you can still merge them together and sort them, even with that 5th shard being down. It does mean, for a while, your users get slightly worse relevancy, though generally, it's okay. And that's a really great idea. That's the kind of stuff that we can do because we have many more machines, because we've distributed them. We don't have to just crash the app whenever one thing goes wrong. And you can actually go further with that, which is really cool, and a lot of search indexes do this, where they actually bound the amount of time a search index process will actually spend reading off disk or in memory for a given query, and then exit whatever most relevant results they have at the end of 200 milliseconds, say. Probably close to like 20 milliseconds, but whatever. It's great. It's a good trick. We should do that kind of stuff all the way down. If you can build out such that your users can still use your stuff, but maybe it's a little bit shittier, that's okay. And I'm going to combine, so who to follow the monorail? The monorail is our name for the legacy monolithic Ruby on Rails app that we have at Twitter. Monorail. It was this guy, JP, named it a while back. It was perfect, because we used to call it Twitter or .com, but .com ran a whole bunch of other stuff, and so it was really unclear what you're talking about if you actually meant the website. But Monorail's great. Monorail's like a big ball of mud web app that like you kind of like turn into a thing that has daemons and a whole bunch of other stuff. Strongly recommend using it in your company. We were adding the who to follow service. This is one of the very first external services that were not just a database to the monorail. And when we did this, it was something like, the timeout was like a second or two, and we had given the monorail, it would get like 5 seconds to process all of its work before we'd say, you get a fail whale. And it was actually a 502, not a 50, or no, that was 503, anyway. So it had a pretty high timeout, which meant if it started having problems, we would sometimes timeout requests on home timeline or something like that, because what we were doing is we were putting who to follow suggestions of who you should follow to the little like top left of your home timeline. And you see it right there and see, oh, cool, those people are great. And it was super engaging. We got a whole bunch of people love it. And then, but if it would go down, you get a fail whale. And then we were like, wait, wait, we don't actually have to fail whale when this thing goes down. What you can actually do is you cut out the little section if who to follow didn't return in time, and make the latency shorter, and then you just don't display that section of the page. Like, why? That's optional. It's totally, like, why would you display something if it's down? Like, we don't need it. It's not required. And that's the kind of decisions that you have to make and be thinking about, that maybe your system is not going to make or break the company if it doesn't show up. And of course, you got to have all the stuff in the right place to do that, but it works. So I'm going to consider, let's suppose you're adding like a private messaging feature to your social website. You've got some inbox thing, direct messages, whatever. You have a decision to make when you're talking about partial availability. There are 2 ways you can do this. You can say, okay, let's suppose a shard went down. Maybe that should mean that for some fraction of our user base, they just can't access their private messages. That means that we have centralized all their messages onto those machines or onto some set of machines, that if they went down, we're just out of the game. That's okay. Alternatively, maybe that should mean that if enough of those machines go down, that everybody should lose some DMs, right? If both replicas go down, maybe that just means like everybody all across your site just loses tweets. You don't know why. And those are the kind of decisions that are not actually infrastructure system decisions. They're product and business decisions. Like, they're actually like things that we as distributed systems engineers need to be aware of and think about as we're going into production, because they affect how people see your site, how they use it, how they address your problems, what kind of revenue streams you can build out, like all of this stuff. And it comes back to not only product people and engineers who can make pretty stuff, but us in the back end trying to get work done and trying to make it so that they can do all that stuff. Okay, I'm going to bring this back into systems engineering. Back pressure is absolutely critical, and it's something that we don't see enough of, especially in the open source world. You don't even know that it exists until somebody sends a patch in that's very large. Back pressure is the idea from plumbing that there are parts of the plumbing system that can't handle all the water that could theoretically get pushed into them. That you could have a little pipe with weak bolts that could suddenly get a torrent because of a flood or something coming into those pipes. And so you have to build a little flange or a little doodad or route some water around and come up with like interesting sliding mechanisms in order to make it so that the water is pushed back instead of being flooding through the smaller system. And this has an obvious example of back pressure is defining a fixed size queue that all of your work gets added to as an object, and then you pop off the top and you say, or the bottom, whichever one you like, the work to actually be done, but you have a fixed size that you know that your system can handle. Now, new engineers, when they come into distributed systems, they see APIs like link blocking queue or array blocking queue in Java, and they see that the default constructor gives you max integer number jobs, that you could put as many objects inside the queue as you want. Erlang has what I consider one of the one or maybe two. Every programming language has sins, and Erlang's sin is the unbounded queue inside of each process, their message box. Because unbounded queues are awful. They will fuck you up, and they will fuck you up way, way, way after you write the code. So here's what happens with an unbounded queue. An unbounded queue, day to day, kind of goes like this. And it uses up some of it, but not a lot of it, and then it kind of goes away. Great. And then you start getting more traffic or whatever, your system just gets more popular for whatever reason. You get more engineers to use it, and it starts going like that. And you're like, okay. And maybe you put like an alert in there, so if it gets really big, you like, oh, whoa, whoops. But everybody gets used to that alert, so you keep pushing it out further and further, that alert, because it's not actually affecting anything. And then one day, you start getting weird GC problems, or like your heap is like suddenly fragmented, and you don't know why. Like, what's going on? And it's because 6 months ago, you wrote this thing that's now smacking up against the constraints of your system, because an unbounded queue, while it looks unbounded, is bounded by the resources of your process, and more importantly, the resources in your system, and you have made them implicit, not explicit. And making things implicit in distributed systems is a quick way to fuck yourself.
What are the odds someone else is maintaining it by then?
Right. That's worse. So another thing that happens is like you get into GC spirals where you take down not only the subsystem that was involved in that unbounded queue, but you take down everything else that was around it, where you might have this might be a side thing that was just supposed to be done like asynchronous, lazy, whatever you don't care about, but now your entire process that may be running critical code is just done, and you're out of the game. And you start having a whole bunch of things. This also applies, by the way, to distributed queues, which is distributed queues and memcache are the most abused pieces of software in distributed systems today. You can walk down to any company in Soma, and they're using both of them, and I think they're both massive mistakes. They're both basically used because we don't have because distributed databases are about 5 to 10 years behind where they need to be for us to actually use them well. Maybe 1 or 2 if we work really hard. And that's a thing. And I mean this, actually, RICON is one of the, it's a sponsor, so I have to say nice things about it. RICON is one of the companies that I actually have a bunch of people I know at, in part because they think about this stuff a lot, and they want to make it better. But not everything is there, not every use case understands it. Okay, so what can you do for back pressure? We have fixed size and allocations, which is really dope. The fixed allocation trick, if you read about this thing called the disruptor pattern, which is like the the extreme idea of that, where you basically allocate just enough memory that you'll ever be able to handle in the process, and if you ever need more, you reject the message. You can also drop messages on the floor, hopefully with a stat that gets anchored, so you know you're doing it. And then you also can return undocumented overload errors. Scribe does all these things. You say like OK or fail, and that's the entire API. And of course, related, though not quite back pressure, but timeouts. Not just socket timeouts, but timeouts on how long you're willing to spend on CPU or wherever on disk, and then kicking out when that's not working anymore. Because you may have a bad disk, you might have slowness, and you actually need to know that things are going poorly and minimize the problem for all the users by maybe making one user have a worse time. And that doesn't, I mean user by both clients of your software, people sitting in desks, but other systems that are using you. Okay. Now I said earlier that I included the wrong word in a slide, and I said deploy, and everybody understands deploy as code release, where they are the same thing. They are not the same thing. We should adjust this. We should change our thinking on this particular problem. What do I mean? That means that when you put your code out onto your machines and you restart the processes and you bring them up, that should not necessarily be when that new code you were shipping starts being used by users. Let me give a concrete example of this. You should roll out infrastructure with feature flags. Feature flags are most commonly known in the A/B testing world, where they were used originally to actually determine by percentages how many users should see user interface 1 versus user interface 2. And those are different things. However, it turns out that's also super dope for figuring out what piece of infrastructure you should use. And that means if you're replacing a database with a new service or an old service with a new one, you should have a decider in place. Excuse me. We'll get to the decider thing in a bit, but you should have a feature flag in place to migrate you over. I've seen too many big projects fail, take way too long, because they went and they tried to have a big bang release on a Thursday afternoon, and they have to get their shit reverted, or it's super buggy for weeks, and they have to do all hands, the entire company having to spend time on this thing. And this applies even if you're like 5 or 10 people. This is scale invariant, because you will break stuff, and it will be hard to fix those things, especially if you've decided that this is the whole big key. So what you're going to do instead is you're going to do slow, dark rollouts. Load testing is important, profiling is important, but there is nothing like production traffic. And if you can slowly ramp up the traffic to the new system while not actually using the output of that system to the user, it's great. In parallel, you do system A query, system B query, and you have a decider saying how many system Bs you should have so that you don't overwhelm system B that maybe is a raw new prototype and you just want to build it out and see what happens. But you can turn off with a flick of a switch. Or this has totally happened at Twitter and other places that I've seen where you suddenly realize that you have a lot less capacity on system A, on the old system, and you really quickly need to just make system B that night the new priority. It happens, and it's great. That kind of flexibility is what you get when you separate deploy from release. And so it kind of looks like this in your code. We have this thing called decider that is basically our implementation of this. It does a bunch of stuff, including you pass in like the name of the feature, which is like, I don't know, retweets or whatever, and then user ID or just a random number, and that actually does some modulus work underneath the hood by hashing in the key name and yada, 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 to figure out if the if statement should go to true or should go to false. And you have the same code path right there. And now a lot of people, when they're fresh and they've not seen this kind of thing before, especially if they're like classically trained engineers or fresh out of college, they see a lot of if statements, and they kind of start having conniptions of like, if decider available, this thing, and then that thing, and they're like, yeah, okay. Because it clutters up your code base. You can really get bad. And then we're like, yeah, we'll clean it up, and you can kind of push it behind policy objects, and you can do the stuff where like, you kind of like make an anonymous function in case where it makes sense. But you actually, they really get bothered by the complexity that these if statements are adding to their code. And at a certain point, I had to have a conversation with some folks where I said, look, these feature flag things, we have to accept the local complexity in order to get global resiliency and simplicity. And that's the difference between like a distributed systems engineer and like a systems engineer, where like we actually have to make a trade-off in our code where it looks worse, where it is more hard to understand, so that overall, everybody who's using the system and us at 3 in the morning when we need to turn something off can do it. And that's a trade-off. And that's weird, and that's unusual. And that's one of the things that are new and hard about these things. The last part is canaries. This is another separating deploy release kind of ish. An initial, everybody knows about the canary in the coal mine, which is you take a canary into you while you're mining a coal mine, and if the canary dies, that means there's poisonous gas around, and you need to get the hell out of Dodge, because it'll die first. And so canaries in the release world typically means you deploy to some percentage, some small percentage of machines, check out that the stats are okay, that the metrics look good, that's log, yada, yada, yada. Maybe you kick it with a couple of, like a bunch of QA tests. And that's a good idea. And you should totally do that. It's a great thing. But on the other hand, there's this other thing that is very empowering and that some companies actually fight against, and to I think their detriment, and new engineers don't know that they can do, that I want to make sure that they know that they can do this. If you've got your code reviewed by other people who are, and you're ready to go, but you need to test if it works or not, you can actually just deploy to like one or a couple machines and like actually see what the stats do and see what happens. That's actually allowed and okay. And that is a common thing that I've actually seen engineers not do and then you give them that ability, you teach them how to do the deploy, their mind like opens up because there's so much power and so much responsibility that we're giving them that their whole system gets better because of it. Their work takes shorter to get done. We can have interesting things happen. It's really good. And we should stop being scared of it and instead embrace it and make it easy to do audit trails and make it easy to deploy and make it easy to pull back things and see what's going on. And what these feature flags and canaries mean is that multiple versions of everything is the norm. You can have two systems that are doing the exact same kind of job. You can have two systems that are different versions of the exact same system. You can have data that lives in different places that are the same. And it's okay. That's okay. It's not ideal in all cases, but it's okay. It's allowed. That's actually how you get better, is by allowing that kind of change and mutability to exist in your system. Okay, a lot of this has been predicated on the idea of services. And so we're at about 30, oh God, is that 238? Oh, okay, so extracting services is a really good idea. You should do it. Don't extract client libraries. Client libraries sound like a really good way of sharing code up until the point when somebody tries to cheat by looking into the internals of your library, and they will dig out guts, and you have now a harder time and you need to upgrade them because they're dependent on exactly how your internals work, and you can't do it because they're using it, and now you're SOL. Or it just takes like an extra week. Pulling out services makes deploys easier to do. How many times have you had to like shut down all the network connections to a database just so that you could change a schema or do something weird, or like do slow warm up on every boot because you had some system that needed it? And every time you put all those code bases together of libraries being shared in one process, that means the complexity of the actual deploy and boot and edge case behavior happens on every single machine. Plus, you have a ton of more machines that need to do that instead of maybe you build out a user service that has all the things that you need to know how to modify and get a user. And that is on 4 machines instead of 40 in every single web app. And you can iterate on that super fast. That's much easier. There's a little bit of tricks, but you can do it. The last thing is I hinted at this with the first one. Libraries require human coordination because even at like 10 people, you actually have to get the other person to prioritize upgrading your library in their code. You're not necessarily like all in the same code base. You're not all necessarily working the same problem. You actually might be like, you actually have to go convince them, and they have different priorities. Like, it's true, and then start getting bigger, and you got to like go cross teams, and like there's whole different corporate goals and all this other stuff. No. Screw that. Let's go to service-oriented architectures, because then at least you have a guarantee that you're backwards compatible, and if you break somebody, assuming your service exposes a schema and yada, yada, yada. Oh, one last thing. I'm using service in a very Twittery way, and that means like a request response remote API, generally request response, and some people are taken aback by that choice of definition, but I don't know, it seems to work for us. The last couple of things here is you need to standardize. If you don't have one way of getting metrics out of your system, or at least a small number, you will never be able to understand what those other systems are doing. Because distributed system problems never just exist in your system, they exist in everybody's system. And you actually, in order to localize them, you need to be able to dig in to everybody else's stacks. This is why I think, no, I'm not going to say that. Fuck it, hold on a second. Okay, polyglot companies are bullshit. Sorry, you can't ship. You have one dude who can ship that particular language, and that's it, you're dead. You're bust. As soon as that dude decides to quit, gets really mad, you're out of the game, because you have to go implement the stuff. Because it actually takes a while to learn and get good at any runtime. And I don't mean language. Language is not the problem. Runtime is the problem. There's a whole bunch of other stuff that comes in, and you need to standardize onto a certain number that you are comfortable with as a company. And that doesn't mean that you like write fucking Java turning into JavaScript. It's not what I'm arguing for. Like, you find what is good at things, and you pick them, and you use them. And that's okay. That's okay. We're not all, like, it's allowed. Like, because this isn't, distributed systems are one of the places in which software becomes a little bit less of a craft, and certainly not an art, and becomes much more of a discipline that you actually have to adhere to. Okay. Speaking of discipline that you have to adhere to, on-call rotations are great because they give you a set start time and a set stop time in which you have to freak out at 3 a.m. every day. They're great. They're mentally healthy. They're good for your employees. They're good for you. On top of that, man, I'm running right out of time. I'm so sorry, guys. They also give you, you want specific on-call rotations so that every engineer doesn't have to actually know everything about the system. I was one of the notorious EOCs, engineering on call, about 3.5 years ago. That was awful because I was on call for everything, including code I didn't even know existed. And that happens way quicker today than it has ever happened in software's history, where there is code on machines that you don't know about. And you cannot be on call for those things. It's just not a real thing. There is no engineer that is good enough to be able to do that. We have a hard enough time understanding how our code goes from method calls and functions into kernel writes on disk. Like, how am I going to do this with everybody else's machines? Okay, and I'm going to end real quick by stretching my thought leadership out. Boom, service discovery is super, super important and will become more important. People do this because EC2 exists, because I'm going to talk about Mesos in a little bit. You need to, instead of having host files that contain all of your hosts and the ports that the service runs on, shipped to every single client that you ever need, you just say there's a path in Zookeeper. I'm seeing a clap back there, yeah. You need a path in Zookeeper that tells you what hosts have registered, or DNS with some fancy DNS parsing at the end to tell you what machines are actually up and live and servicing that traffic. Of course, the client has to do their own work of killing off machines that they can't talk to because switches exist, yada, yada, yada. But like, it's an actual thing that we should do less of, because you need to avoid human coordination when all you want to do is add 5 machines. We need some more capacity. I have to go talk to 10 teams and get them to update their config files. Even if you're all in the same repo and like you can just grep for it, there are surprises. And people do interesting things with their like client creation stuff that even when you're standardized happens. It's a thing. All right, so a couple more things. One is Docker and Mesos are the future. They're actually the past for Google. There's this thing called Borg. I suggest you read up on it. It's a data center operating system. Mesos is our open source version that we, Twitter took a couple of folks out of Berkeley. I think we let them finish their PhDs. I'm not sure that they did. But they were working on it at Berkeley, and then we made it real, and it's in production today, and actually attribute a great deal of our success in a lot of my teams to the flexibility that Mesos provided. Because an operating system is a thing that schedules threads and code to resources like CPU and memory and disk and network. And a data center operating system like Mesos, like Borg, are doing the same thing, but for machines. And you say in our job configs, you say, I need this many machines, and I need this much CPU on each, and I need this much memory, and this much disk, and soon, relatively soon, this much network I/O. And you go from there. What's great about those things is once you combine with service discovery, you can just get your job on any machine that's free. And you actually share machines with other services, which is great for a lot of reasons. That means, one, you can run more instances of your code, which is better for your reliability and better for your availability. If any one of those machines goes down, that's okay. It's a much smaller fraction than what we do today, which is we allocate an entire machine for this service, or a couple, and we say, this is the machine, and we put it into Puppet and a Chef. We have some role thing. We like say, there, these are the like platonic ideal of this service. But instead, we have shared resources doing smaller, which usually means that they're faster because the heaps are smaller, doing less work, but on more machines. It's great. It's awesome. We should do more of it. This is actually how you ship distributed systems, and this will become more like it. Docker's the piece. There's also Google just open sourced another thing I can't remember the name of. It's got a really weird acronymy name. And it does Linux containerization. There are some people in this front row who know a great deal about that. Okay, the last thing is, if I ever hear a software engineer talk shit about something being bad because it was, quote, political, I will fucking scream. Collaboration is politics. Agreement is political. You actually have to engage with people and A, have empathy, and B, be able to communicate so that you can get your job done. We're distributed systems engineers. We can do this all fucking day when it comes to machines, but we're not willing to do it when it's like people. I think there's a problem there. Like, most of our work is not technical, it's getting social stuff. You want your distributed system to ship? Cool, you gotta get people to use it. Let's talk about that. And productionization isn't just about this stuff, it's about collaborating with folks to migrate them on. If you don't have a migration plan, you're not productionizing. That's the deal. Like, if you don't have a way for people to get in, if you don't have a feature flag for them to add that you can just crank up and down so that when they get really mad, they can just turn it off, you're screwing up. Okay, and I'm so out of time, I'm like 2 minutes over. That's it. And can I take questions? Okay, applause. Okay. Thank you. Okay.
Explain your retry strategies.
Retry strategies. So anything involving a write, no go. Of course, if you know that your API call is a read, you can retry it. But what we typically do is if it's a socket write problem, if it didn't, like, the connection no longer exists and it was a socket write issue, we'll retry it, and otherwise, nope, it doesn't count it. And that's just how you have to. You can also do tricks that I don't want to step on Jeff Dean's talk, but he does really interesting things where they query 2 machines and they cancel 1 request, and that's a real trick, but it's an advanced maneuver that doesn't support it in a lot of protocols. Hey. Oh, yeah. So Decider, yeah. So Decider actually is a coordinated core piece, but typically integration points are in each service individually, so we typically have a different Decider for each, because each system uses the service in a slightly different way.
So if it goes down, then everything just turn on?
Yeah, you turn everything off. Yeah, that's actually, like, you do have to go through like 3 or 4 whatever deciders that you have. But that said, it is coordinated, and you could have one decider, and people have done this, one decider feature flag for all the systems. That's like the big global one, and you just shut it off and make it go away. Yeah. Okay. Good? All right. Thanks, guys.